Good day. This is part two of our presentation, and together with my partner, we're going to present the theorem.
Theorem 7. Two lines perpendicular to the same plane are parallel. And conversely, if one of the two lines is perpendicular to the plane, the other is also. So let's look for a figure. Figure is a good representation of theorem 7. So these two poles here is our two lines. These two lines are perpendicular to the plane, which is the table. So as stated at theorem 7, the two lines perpendicular to the same plane are parallel. So if these two poles is perpendicular to the table, so it could also be that these two poles are parallel. And conversely, if one of the two parallel lines are perpendicular to the plane, which is the table, the other is also. So that's all. Thank you.
Theorem 8. If a straight line is parallel to any given plane, then it is parallel to the intersection of any plane through it with a given plane. Now, we have a figure here. Let's consider this two planes intersecting this plane and this one. If this plane has a line, this one is the edge. If this line is parallel to the plane, this wall, then this line is parallel to the intersection of these two walls.
Theorem 9. If each of the two planes is perpendicular to the same line, they are parallel. And conversely, if one of the two parallel planes are perpendicular to the line, the other is also. So to prove that this floor is parallel to the ceiling, so to prove that we have to have a line. So this pillar here represents our line. If this pillar is perpendicular to the ceiling, it can also be perpendicular to the floor. So as what the theorem 9 says that if the two as what the theorem 9 says that each of the two planes are perpendicular to the same line are parallel. So as what I said earlier, that the ceiling and the floor are perpendicular to the same line, which is the pillar. So this also means that the ceiling and the floor are parallel. So that's all things. Theorem says, if a plane is parallel to each of the two intersecting lines, then it is parallel to the plane of this line. So let's prove that the floor and the ceiling are parallel. So to prove, we need two intersecting lines. So let's assume these are two intersecting lines that lie on the plane which is the ceiling. So as what the theorem says that if a plane is parallel to two of the intersecting lines, they are parallel. Diba?
Yeah, okay.
Theorem 11. Through a point not on a plane, there is one and only one plane parallel to this plane. So we have our given plane, which is our floor. And we also have a given point. That point is our point. So according plane. So this point or this pool is not on the plane or floor. So to prove theorem 7, we must construct or determine another plane. So this point here, we construct two intersecting lines. So according to theorem 2, in determining plane, we need a line and a point not to keep two intersecting lines and two parallel lines. So we have here two intersecting lines which can determine. So we have now a plane that passes through our point, which can be parallel to our given plane, which is the floor. So that's it. Thank you.
Theorem 12. Through one of two skew lines, there is only one and only one plane parallel to the other line. So let's have two skew lines. This line is our first skew line, this edge of the wall, and the other one is this metal thingy here. This can be our second skew line. And through this skew line, there is only one plane parallel to this skew line. So this glass window that contains this line is the one parallel to this skew line. Theorem 13. Through a point, not on two non-parallel lines, there is only one plane parallel to both lines. So we have two non-parallel lines. Let's just assume that these two and this one can be lines, and they are non-parallel. And through a point which is there, it is outside the non-parallel line. This point, which can be passed through by a plane. And this plane can be extended there because it's infinite. A plane is infinite. So, through this point, and that has a plane through it, it can be parallel to these two non-parallel lines. Theorem 14. If two intersecting lines are parallel, respectively, to two intersecting lines in another plane, then the planes are parallel. And the actual form is the two intersecting lines are equal. Let's suppose that this edge of the coaster, these two edges, are two intersecting lines. And they are parallel to these two edges and this coaster. So these two intersecting lines are parallel. And it is stated that if these two lines are parallel, then the plane that is determined by these two intersecting lines are also parallel. So this wall and this wall is parallel. And also the angle formed by these two intersecting lines, which is the edges, are equal.
Theorem 15. If two straight lines are crossed by three parallel planes, the intersected segments on the other line are proportional to the corresponding segments on the other. So we have our illustration of theorem 15, or the building. The two straight lines represent our two pillars. So these two pillars are capped by three parallel planes, which is the floor. So the segment, which is made by the planes, are proportional to the segments made by the planes below. So the segments below and above are proportional. So that represents our theorem 15. Thanks.
Dihedral angle. So, you see here a plane, which is a plane, then a layer of and then a line in it. So, the plane that is on the other side of the left is called a half plane. And let's consider that there are two half planes, this one and this one, and it meets in this line. So, this forms a dihedral angle of this one. This is the dihedral angle. This half plane is called the base of the dihedral angle. These two are the bases. And the line that cuts, or the line that where it meets, then this line is called the edge. We can aim the dihedral angles by their measures. For example, it forms a 90-degree angle, and it can be called a right dihedral angle. And it can form a angle that is less than 90 degrees, then it can be called a acute angle. And if the angle forms more than 90 degrees, then it can be obtuse, like this one. I'm not sure it's 90, but I'm sure it's more than 90 degrees. So this can be called an obtuse dihedral angle. And it can also be called complementary if they are based on 80, and complementary if there are two dihedral angles 90 degrees, and they can be also called adjacent. That's all. Thank you.
Two dihedral angles are equal if their plane angles are equal. And conversely, if two dihedral angles are equal, their plane angles are also equal. So we represent this theorem 16 by this word, or this word. This is our half plane and half plane. These two half planes meet at this edge. So these two half planes create a dihedral angle. So we need two dihedral angles. So to the other side, this is also the half plane, and this is the half plane, and these two half planes meet on this edge. So these two half planes represent or create a dihedral angle. So to prove or represent the theorem 16, we must know the measure of their plane angles. So we must measure the plane angles of these dihedral angles. So using our protractor. So okay, we'll measure this. As you can see, the measure of this plane angle is 90. So this dihedral angle is the right dihedral angle. So we must also measure the other side. So you also see that it's also 90 degrees, so it is also a right dihedral angle. So this proof our student 16, thank you. So these two dihedral angles are equal because their plane angles are equal. So that's
There's 17. If two planes are mutually perpendicular, and if a line is drawn from a point to their intersection, then this line is perpendicular to the second plane. And we should present it with a figure. Let's suppose that these doors form a plane, and the floor is perpendicular to this door, and the floor is also a plane. And they are perpendicular to each other. And this is it. And this is the intersection of each line. If from a point we draw a straight line to make this line, let's put the line, to make it perpendicular to this intersection. Now, this intersection is perpendicular to this line. And this line lies only on this plane. This line is perpendicular to the intersection. And if this line is perpendicular to the intersection, then this line is perpendicular to the plane. Theorem 18 states that if a plane is perpendicular to two intersecting planes, then the plane is also perpendicular to the intersection of the two planes. Now, look up. See, we have here a figure. This figure, let's suppose that these two bars are the two intersecting planes, and the ceiling is the plane 2. And now, if these two bars are perpendicular to the ceiling, then the intersection of the two bars is perpendicular to the ceiling. And the ceiling is the plane, so the plane is perpendicular to the intersection of the two